In this video, I will walk through a practice problem using Kirchhoff's laws to analyze an electric circuit. We will focus our attention on a circuit with 3 branches and 3 unknown currents, which is one of the most commonly encountered problems when applying Kirchhoff's laws in introductory physics. To be more specific, we will look at this circuit shown on the screen. I will show you step by step how to set up the equations and solve for unknown currents. I will call the branch on the left branch 1, the one in the middle branch 2, and the one on the right branch 3. We will assume that the 3 batteries have these values for their EMFs or voltages. We will also assume that the 5 resistors have these values for their resistances. Our goal is to find the 3 unknown currents. The first step is to calculate the total resistance of the resistors in each branch. Although this step can be skipped, it helps make the circuit easier to analyze. Let's look at branch 1. Here, resistors A and B are in series, so their total resistance is just the sum of their resistances. I will call their total resistance R1, which is equal to 3 ohms, and replace the 2 resistors in the circuit diagram with a single resistor R1. Branch 2 only has 1 resistor, so there is no total resistance to calculate. But for consistency, I will relabel it as R2 instead of RC to remind ourselves that it is the resistor in the second branch. The value of R2 is the same as that of resistor RC, or 3 ohms. Let's now look at branch 3. In this case, the 2 resistors are not in series because there is a battery in between. But because there is no junction between the resistors and the same current flows through them, we can treat them as if they are in series and calculate their total resistance as the sum of their resistances. The total resistance, which I call R3, is RD plus RE, and it is equal to 9 ohms. We can now replace 2 resistors in branch 3 with a single resistor R3. You can see that our circuit is simpler than what we had because we have fewer resistors now. The second step is to define the assumed direction of the current flow in each branch. The choice of the direction is arbitrary. If the actual current flows in the opposite direction, it will result in a negative value for the current. I will call the current that flows through branch 1 I1 and assume that it flows upward through the battery with voltage E1. In branch 2, I will assume that the current flows downward and call it I2. In branch 3, I will assume that the current flows upward through the battery with voltage E3 and call it I3. In this type of problem, we need to use Kirchhoff's junction rule once and the loop rule twice to obtain 3 equations so that we can determine the 3 unknown currents. So in step 3, we will apply the junction rule. The junction rule says that the sum of all the currents flowing into a junction is equal to the sum of all the currents flowing out. Let's look at the junction marked by the red circle in the diagram. As you can see, both I1 and I3 flow into this junction, while I2 flows out of it, making the junction equation I1 plus I3 is equal to I2. In step 4, we need to select a closed loop and apply Kirchhoff's loop rule. I made a video that provides a simple explanation of the loop rule. I encourage you to watch the video after this one if you want to learn more about the rule, including the sign convention. I will choose this large loop starting from the top side of the battery on the left and choose counterclockwise for the direction. The first circuit element we encounter is the battery on the left. According to the circuit symbol, the battery's positive terminal is on the top and the negative terminal is on the bottom. As I move across the battery, I go from the positive side to the negative side, so the voltage change for the battery is negative, or negative E1. Next circuit element I encounter is resistor R1. There's no junction between the battery on the left and R1, making the current through R1 equal to I1. So Ohm's law tells us that the voltage difference across the resistor should be I1 times R1. Question is whether it should come with a positive sign or a negative sign. To determine this, we need to remember that current flows from a higher voltage to a lower voltage. Because the current flows from right to left, the right side must be at a higher voltage than the left side. So as I move across the resistor, I go from low to high voltage, making the voltage change positive. And the voltage change for the resistor should be positive I1 times R1. The next circuit element I encounter is resistor R3. This time, current I3 flows upward. Again, remembering that the current flows from high to low voltage, we can identify that the bottom side of the resistor should have a higher voltage. This implies that as I go across R3, the voltage decreases, making the voltage change negative I3 R3. Lastly, it is the battery with voltage E3. The battery has its positive terminal facing up and the negative terminal facing down. Moving upward across the battery, I go from the negative side to the positive side, which is an increase, so we get positive E3 for the voltage change. Now that I am back where I started, I can say that the sum of all these voltage changes is equal to 0. So this is the equation I get for loop 1. In step 5, we need to choose a second loop and apply Kirchhoff's loop rule. I will choose this smaller loop, starting from the same location as before and moving in the same direction, which is counterclockwise. Because the way I travel across the battery with voltage E1 and resistor R1 is exactly the same as how I traveled when we analyzed the first loop, the first two terms are exactly the same as the equation for loop 1. For the battery with voltage E2, I move from negative terminal to the positive terminal, making the voltage change positive E2. Lastly, for resistor R2, the current flows downward, which means I go from low to high voltage, making the contribution to the equation positive I2 R2. Coming back to where we started, this is now equal to 0. We now have 3 equations. Since there are 3 unknown currents, this gives us a complete system that we can solve. So in the last step, we solve the 3 equations simultaneously to determine the 3 currents. Let's call the first equation J because we got it from the junction rule, and the second and third equations L1 and L2 because we obtained them from loop 1 and loop 2 respectively. Let's simplify L1. Plugging in the values for E1, E3, R1, and R3, we get this equation. We can simplify this by combining negative 2 volts with 4 volts to obtain this equation. This is now an updated version of equation L1. Similarly, plugging in the values for E1, E2, R1, and R2, L2 becomes this, which can be simplified to this equation. This is an updated equation L2. There are different ways to solve these 3 equations simultaneously. Here's one way. First, we look at L1 and L2 and identify a current that's common to both equations. In this case, it's I1. Next, we solve each of L1 and L2 for the other current. For L1, the other current is I3. Solving this equation for I3, we get this equation. For equation L2, the other current is I2. Solving this for I2, we obtain this equation. We can now substitute these results we just obtained for I2 and I3 into equation J, which then becomes this. Notice how this new equation boxed in orange only has I1, which means we can solve it to determine I1. After some simple algebra, we find that I1 is equal to negative 0.238 amperes. Now that we know the value of I1, we can plug it into the equation boxed in green and show that I3 is equal to positive 0.143 amperes. Finally, we can plug in the value for I1 into the equation boxed in purple and find that I2 to be negative 0.095 amperes. Now that we know the values for the currents, let's think about their directions. Here's the original circuit diagram. We assumed I1 to flow upward. Because I1 turned out to be negative, this means that the actual direction for the current is downward. For I2, we assumed that the direction to be downward, but the value turned out to be negative, so I2 actually flows in the opposite direction, which is upward. Finally, I3 came out to be positive, implying that the direction we assumed originally was correct, so it flows upward. Thank you for watching. In the next video, I will discuss equations that can be used to find the currents for the same problem, but without using Kirchhoff's rules.